This is a really neat proof of the Pythagorean theorem. This is credited to the Hindu mathematician Bhaskar. So I wanted to walk you through this, and this is written out in your reading, but if you'd like to kind of hear out the steps, I thought I would just do a video of this to show you how this works. Alright, so this is presented in your reading as a deductive proof. And one of the things that's maybe not clear, the definition of a deductive argument was given as something that moves from more general type principles to something specific. Right, so I want to be clear here, this is not necessarily general to specific in the sense that you might have seen in the other examples, but this is deductive. Maybe another way to say it is that this is starting with things that are already known, and we are making a valid logical chain of statements that leads to something else that's known. Right, so this would kind of take that form: if P then Q, if Q then R, and we may need many of these statements. Okay, so like if R, then S, dot, dot, dot. Okay, and then what we'll eventually end up with, hopefully at the end, is being able to conclude our statement here, the Pythagorean theorem. Okay, so keep that in mind as we go through this, and you can kind of pick out maybe some key facts or formulas or things that you've learned in geometry that are already known and convincing bits of information. Okay, so what we're starting with is a general diagram here, and there are no numbers, which is really important when you're trying to show that something's true deductively, because as soon as you put specific numbers in here, then that becomes an inductive argument. Okay, so you'd be looking at examples, like triangles with 3 and 4 and 5, and trying to conclude some sort of a general statement based on those specific examples. Right, so by staying with just the letters A, B, and C to represent different lengths, we're trying to keep this really general. All right, so the first fact we have is actually this diagram itself, and we just have this square that's kind of arranged with 4 triangles around it. Right, and we can do that. We can just start with some sort of a figure here. This is not a proposition because it's not actually saying anything. It's just a diagram. Okay. Now this thing at the top here, this equation, this is a proposition because it's got a verb. It's got the equal sign, and this is making some sort of a claim. Right. So the claim is that the area of the large square, right, this orange thing, is equal to the area of the small square plus the area of these 4 triangles. Okay, so we didn't prove that statement because it's kind of obvious, but you do kind of have to believe that the whole is the sum of the parts there. Right, so this is an assumption, but we all kind of accept that those little smaller areas add up to the larger one. Okay, and then from there we use some different facts from geometry. All right, so one thing you need to know is how to find area. All right, so area of squares, I'll call this, we'll just say area of square. Okay, and the area of a square is just the base times the height, right? Or you may have learned it's the side times the side. All right, so for this little square, okay, well, what's its side length? Right, well, that would be A minus B. Okay, so let's back up a little bit even further. What are A and B? Let's orient ourselves here. Right, so in any one of these 4 triangles, we have A is this longer side, and then we have B is this smaller side. Right, so if you look at this length here, this is the long side of a triangle, so that's A. Right, and then if you subtract away B, this shorter length here, okay, notice that's the shorter side of a triangle. Right, well then what's left, we can just call that whatever A minus B is. Okay, so the area of the smaller square is A minus B, one of its sides, times the other one of its sides, A minus B. Okay, we need to pull in a little bit of algebra to find what that is, but we'll leave that for now. The area of the larger square is a little bit easier because we've just called the side length C. Right, so the area of the larger square is just C times C. Okay, and then what do we do with the area of a triangle? So we need another fact from geometry, and we can find the area of a triangle by doing its base times its height and dividing that in half. All right, so for each of these triangles, we have its base can be b and its height can be a. All right, so we have a times b, and then we divide that by 2. All right, so that's the area of each one of those triangles. Right? So notice again, we're using things that are previously known. We're assuming that those have been, proven geometry facts that we can assume going into this proof. All right, and then we take that information and we put that into this equation at the top. All right, so the area of the large square we said was c squared, and that equals the area of the small square, which is a minus b times a minus b, side times side, right, plus 4 of the area of the triangles, which we said was a times b divided by 2. Okay, and then our goal is to just try to use algebra facts now to get this to look like the Pythagorean theorem, which is c squared equals a squared plus b squared. So that's the goal. All right, so what is a minus b times a minus b? Right, you need to know how to multiply from algebra. Right, so you may be familiar with FOIL, right, or the distributive property, and if you're not, you may need to look that up in order for this to make sense. But the gist is that we just want to multiply. We've got 4 things here, okay, a and b and a and b, and we want to multiply each of those things by each other thing. Right, so kind of glossing over the details there, we would get this first a times a is a squared, right, and this first a times negative b is negative a times b, okay, and then we want to go back and multiply this first negative b by a, okay, and I'm just going to write it in alphabetical order, so that's negative b times a, and then this first negative b times the second negative b is positive b squared. And again, you may need to kind of take this on faith if you don't remember those rules from algebra. All right, so negative ab and another negative ab makes 2 of them. So what we end up with is a squared minus 2 ab's plus b squared. Okay, so that's the hard part. And then this second bit, right, we have 4 of these triangles. Right, so we have a times b, and then we're going to multiply that by 4 and divide it by 2. Right, so that's the same thing as actually just multiplying ab by 2. Okay, so plus 2ab. All right, if you're not convinced of that, you can just take a number like, I don't know, like 10, right? And notice if you divide that by 2, you get 5. And if you multiply that by 4, you get 20. And notice that that is just 2 times the original number 10. Okay, so that's why we have 2ab. All right, so cleaning this up a little bit, let me erase some of the work here. Right, and what I have now is that c squared equals this original stuff, and I just showed that that equals this stuff here. See if I can do this. Oops, nope. Okay, I can rewrite that, so that would be a squared minus 2ab plus b squared. Okay, so that's the area of the small square, and then plus the 4 triangles, which turn out to be 2ab. All right, so the last thing to do is to just see that we're subtracting 2ab, and then we're adding 2ab, so those 2 undo each other. All right, and that's going to equal 0. So this just equals a squared plus b squared. All right, and there you have it. We started with c squared, the area of the large square, and we showed that that equals a squared plus b squared. Right, and if we look back at one of these original triangles, there's that relationship that we're looking for, which is that the long side squared plus the short side squared equals the hypotenuse squared. Okay, and that's our proof of the Pythagorean theorem. All right, so again, notice we kept everything really general. We didn't use any specific numbers, And the facts that we used, the propositions you could say, were a couple of area formulas from geometry, and then rules from algebra about how to multiply these types of things with variables and numbers.